Hello everyone, welcome to Idiot Developer. In this video, we are going to learn how to implement UNet 3 Plus, an architecture for medical image segmentation. So whether you are new to this or already know a bit, I am here to help. So let's get started. So first of all, let's understand its basic definition. It is an advanced medical image segmentation architecture built upon UNet++, featuring full-scale skip connections, deep supervision, and a classification guided module for improved accuracy and reduce parameter. The model effectively captures fine-grained detail and coarse-grained semantic in medical images, addressing issues like over-segmentation and false positive. And here below you can see a comparative block diagram of UNet, UNet++, and our UNet 3 Plus. So UNet utilize basic skip connections, whereas UNet++ enhance this by introducing nested and then skip connections. UNet 3 Plus goes beyond by incorporating full-scale skip connection, improving model's efficiency in capturing information across various scale for more accurate medical image segmentation, thus addressing a limitation of both UNet and UNet++. Now we'll discuss its component. Unlike any other architecture, UNet 3 Plus also has two main things, that is an encoder and a decoder. So the structure of encoder is same as that of UNet, while decoder is a bit different and it incorporate both smaller and same scale features from the encoder and large scale feature map from the decoder. So this is the basic difference between the decoder of other, that is UNet++ and this UNet 3 Plus. So we'll learn about it during the implementation. Now its architecture types. So first is its normal UNet 3 Plus. Second would be with deep supervision. Okay, and third with where we gonna implement the classification guided module. So first of all, we have normal UNet 3 Plus. So this is one of the diagram which we have in the paper, and I know this is for deep supervision, but just see this diagram and remove these four supervision blocks. Just see the last one, okay, and that would form the normal UNet 3 Plus. So now we'll start with the implementation of UNet 3 Plus, okay, the normal one, and all this we are doing in the TensorFlow. So first of all, we are going to import all the libraries. So first of all, we have our basic conv block. So it takes your input, that is the input feature map, and this feature map would have a height and width because we are dealing with images. Okay? And second would be number of filter. This basically define number of output channels. Then we have a variable called act, which is by default set to true. So inside this conv block we have convolution layer. After that we have act. If act is true, then the output of convolution layer would pass via the base normalization and ReLU activation function. If it is false, then these two layers won't be added, and you get the output. Now we would work on to the encoder. So encoder of this UNet 3 Plus is same as that of UNet, and it takes your input, that is X, the number of filters. So it has two conv block followed by a 2x2 max pooling, and it give you two output, that is X. So X is the output of second conv block, and it is used in your skip connections. Okay, you remember from the slide what is shows that it incorporate both smaller and same scale feature map from the encoder. So this X would be this feature map from the encoder, and P is basically output of this max pool layer. So now the encoder part is done. Now we'll move on to the UNet++. So we'll define a function called UNet+. So first it has the input shape, then number of classes. So here our number of class would be 1. Next we would define an input layer. This is our input layer. We say L.input, then we give it the input shape. So here our input shape can be like 256 multiply 256 multiply 3. Okay, that is an example. So we can write it here, 256 by 256 by 3. That is an RGB image. Next we'll have our encoder block. So this is our first encoder block. So we say encoder block, then we give the input layer and 64 as a number of filters. Here you can see number of filters. So it refers to number of output channel. And it give you two output, that is E1 and P1. And we name them like this only. So E1 refer to feature of encoder and the P1 refer to pooling layer. So while we are working on the decoder, we can easily refer to them E1, E2, E3, E4, so that it reminds us of the encoder, that E refer to encoder. Next we have three encoder blocks. So now we have second encoder block which take P1, that is the output of pooling layer, as the input and the number of filter to 128, and it give output E2 and P2. So like this we have two more encoder block. So here in the encoder network, you can see the number of filters are increasing by a factor of 2, and the number of not the number of and the fatal dimension of the feature map, that is height and width, would decrease by a factor of 2, because in each encoder block we are using a max pool layer. Now what we're going to do, we're going to simply run this network by printing the values of E1, E2, E3, E4. Now we're going to call our main function here. Okay, let me remove this state. Okay, so this is the shape for our network, and we're going to call our UNet 3 plus, and we're going to give this shape as the input. Now we can run this. Here you can see the shape. Now just observe, this is the height and width, and this is the number of output channel. Here you can see the height and width, it decreases by a factor of 2. Okay, and next you see number of filters, they would increase by a factor of 2. So this thing you would note in any encoder. This is not new here. Now we are done with the encoder part. Now we need to move on to the decoder. So before decoder we have a bridge in between both the encoder and decoder, and that is really simple. Basically I call it bridge in the paper. It's a kind of a part of encoder only. So if you go to the diagram here, you can see the 5 block, x1 E, x2 E. So this E refer to encoder. So first, second, third, fourth, fifth. I usually call it the bridge or the bottleneck, that is the part between the encoder and the decoder, but accordingly I have named it E5. E5, just cone, it has 2 cone block, no max pool. Now we're going to work onto the decoder 4. So basically first decoder, but we're going to refer it as decoder 4. Now see the paper, it says X4DE. D refers to decoder, and X4 basically fourth decoder block. Now if you see, it receives skip connection or features from X5, then X4, X3, X2, X1. So from all it receives features, and it concatenate here. So for concatenation, the shape of all the features should be same. Okay, let's go back to this. So now first of all we'll see how a normal UNet in decoder would work. So we have E5. Okay, so first of all, what would happen, we would have a transpose convolution layer or any upsampling layer to upsample E5. So let's say here E5 is 16 by 16, I think, if you remember, 32. This is E5 is 16 by, let me just print it for you so that we are sure what it is. It is 16. We are sure. So what would a normal UNet decoder would look? First we have upsample, then we have a concat layer with a skip connection, and that skip connection would be E4, because now E5 is upsample, so its size became 32 by 32. And if you remember from shape, E4 is equal to this, so E4, then it is followed by the con block. So this is your simple decoder. So now instead of just having one feature as a skip connection from encoder, it utilizes all of them. So first of all, we'll move to E1. So we need to make sure both E1, E2, E3 should be equal to E4, because E4 is the main skip connection and rest we need to downsample. E4 is the feature map which is of same scale, and rest we need to downsample. So this is what we're gonna do. I hope you get it. So first of all, we have E1. So we say E1 D4. We have a max pool layer 8 by 8. Then we have E1 D4 followed by con block. Okay, and the number of filters here is 64. So this is for the E1. Now we're gonna do E2. See, E1 is of size 256 by 256. So when we divide it by 8, it became 32. Okay, let me open up a calculator for you here. Our shape is 256 and we're gonna divide it by, you can see, became 32. So now our next feature map E2 is of shape 128, and when we divide it by 4, became 32. So like this we have E2. So we say E2 D4, E2 D4, max pool of 4 by 4, then a con block. So like this we have E3rd, and it would have a shape of 64 by 64. So we have a max pool of 2 by 2, then again a con block with 64 at the feature. Now for E4, we don't have any max pool or upsample block. We simply have a con block only. Now these are the four feature map. Now we also have E5. So the shape of E5 is 16 by 16. So in this case, we need to upsample it. Just remember, we are utilizing all the features. Just see this diagram. We are also utilizing E5. So for E5, we are performing a bilinear upsampling. Okay, and then it is followed by a con block with 64 as a number of channels. Now the shape of these E1 D4, E2 D4, E3 D4, E4 D4 and E5 D4 should be same. So to check that, we're going to print each of them. Initially it was a bit confusing, but then if you understand it carefully, it's easy how this is implemented. So if you easily understand first and second, that is decoder third, fourth and decoder third, you can easily understand the rest too. Because this is, I hope this is easy now, but in the next its implementation is same, just a bit difference, and that we'll see. That's shape of all them. So now you can see all of them have same shape and same number of feature channel. It is easy for all these channels to be concatenated together. So now we're going to concatenate them, and after concatenation it is so followed by a con block. So we have concatenation, then E1 D4, E2 D4, E3 D4, E4 D4, E5 D4, and then a con block. Now this is your decoder 4. That is the main D4 refers to the output of decoder 4. Now we're going to run this. You can see the shape is 32 by 32 and 320 as the number of feature channels. Now we're going to move on to the decoder third. Now here in the decoder 4, we need to resize or rescale all the features to the shape equals to E4. Now it would go to E3rd. Now we need to make sure E1, E2, E4 and E5 are of the shape as E3rd. The shape of E3rd, if you see 64. So we did divide 256 by 4. It became 64. That is easy. So we're gonna do the same here. I'm gonna simply copy paste it because typing it would take long, and this video would become a whole 3-hour movie. So now E1 D3rd, max pooling 4 by 4 and a con block. Simple. Same we're gonna do with a E2 D3rd. Same, max pooling 2 by 2, input is E2 and then a con block. Now for E3rd, it would be easy because we are matching the size E3rd only, so no upsampling or max pool block. Now comes to E4. Okay, E4. So now if you see the decoder 4 utilizes E4 as its main feature, or you can say the shape of E4 and the D4 is equal. So instead of utilizing E4, we're going to utilize D4. So that is how it incorporate both in feature from encoder and decoder. So in decoder 3rd, what we're going to do is we do it like this. So we say D4. So we upsample it and then it is followed by con block. I hope you got it now. So if you go back to the definition of this decoder, it says it incorporates both smaller scale and same scale feature map from encoder and a large scale feature map from decoder. So this is what we meant here. And here you can see the same thing in the implementation. Features, small scale and same scale feature from the encoder and large scale feature map from the decoder. Next we have E5. E5 again, this bridge. You can even include it in your encoder part, but I'll most usually refer it to as bridge or the bottleneck. Now we have 5 features here. Again we're going to do the same, concatenate them, and then it is followed by a con block. Now we're going to print D3rd and we're going to run it. So it became 64 by 64 and 320 became the number of channels. So now we're going to move on to the decoder 2. So for decoder 2, the size, the same scale feature map is E2. So first we're going to have E1, E2. So it is max pool 2 by 2 and then a con block. Next a con block just for feature map E2. Next, if we're going to use the feature map from both the decoder, that is decoder 3rd and decoder 4th. Instead of just simply, the principle is instead of utilizing pure encoder feature, now we're going to utilize feature from decoder. See, one of the good thing about these like arrows, these concatenation, these flow of information from connection, is that during back propagation, the gradient travel backward via these connections, and it became really easy. Just imagine that the gradient is going from here, it is going here. So gradient became really small. And if it goes from this x1 DE to directly to x1 E, so this became really easy now. So gradient travel a straightforward path. So this is one advantage of having these skip connections. Let's move back to our this implementation. So we are in decoder 2. So now we're going to have D3rd. We're going to upsample it by factor of 2 using bilinear interpolation followed by con block. Then we have D4 upsampled by factor of 4. Then we have E5 D2 upsampled by factor of 8. Then we have concatenation followed by a con block. Now we have the output of D2. So now you can imagine the size would be 120 by 120. Let's move on to the even. I'll directly copy all the layer of decoder 1 or the even decoder 1. Now we have even D1. So no max pool is required. This is the first feature map from the encoder. Then it is followed by upsampling layer. First is the D2 followed by 2 by 2 upsampling con block. Then it has D third 4 by 4 upsampling followed by con block. Then it has D4 followed by 8 by 8 upsampling, then a con block, and at last E5 16 by 16 and a con block, then concatenation and D1. So now we have all the 4 decoders. Now what we need, because this is first the simple UNet 3 plus, it would have only one output. So now we would have a 1 by 1 conv layer followed by the sigmoid activation. This is okay, it should be 1 by 1. Okay, and num class. So here we have 1 as the number of class, if you remember. So this is a binary segmentation problem. So we are going to use softmax, not the softmax, sigmoid activation. So if you have more than one class, let's say you have 2, 3, anything greater than 1, it would be softmax. So now we're going to build our model. This is simple UNet 3 plus implementation. Not print, it should be model dot summary. I'm gonna run it now. See, we get, you can see we are the last part. Let's go to the starting. Okay, you can see this is the input layer 256 by 256 by 3. Then we have the encoder. You can see this fatal dimension decreasing, number of phase channel increasing, and till here you can see this 1024. It is this is the bridge part, and this is still encoder. Then after it becomes a decoder. So printing the summary simply means the model is working, and it gives you the output 256 by 256. So this is the implementation of simple UNet 3 plus. Next we're going to implement this UNet 3 plus with deep supervision, and that is really simple. It's not that difficult. So what I'm going to do, I'm going to copy this code into another file. So just we need to make few changes in it. Just that till now we are using D1, that is decoder 1, the last decoder, to get the output mask. But now we're going to use all these, that is D1, D2, D3, D4 and E5 to get our segmentation, and that is the change which we need to do. So let's add a variable here. We say deep sup, that is deep supervision is true, then only we're gonna allow it. We just want user to have a choice. We want the deep supervision. So first of all, let me remove it, comment out. So we say deep supervision if it is true. The deep supervision. So now what we're gonna do, first I'm gonna copy the code from here only. The first would be D1. So now in this case you need to remember the shape of D1, D2, D3, D4 and E5. The shape of D1 is equals to 256 by 256, and that is equals to our shape of input image. So now we don't need any upsampling here, so we simply say y1 followed by a con block, then a sigmoid activation. Next we're gonna have y2, that is output of D2. Now let's say y2, y2. Now the shape of D2 is 128 by 128. And if I do this, then the shape of Y2 would be 128. So we cannot do it like this. So what we need to add a upsampling layer here. So we're going to add an upsampling layer between the convolution and the activation function. So like this, we have Y2. Now similarly, we have Y3, Y4 and Y5. So we have Y third, 1 by 1 conv, upsampling and activation, D third. Then we have D4, again 1 by 1 conv, sampling by a factor of 8, then sigmoid. At last we are using E5. We have Y5, 1 by 1 conv, 16 by 16 upsampling and sigmoid. So now we have our outputs. Now just in case the user don't want to use deep supervision, that is else case, so it would be phi1 p1. Now we're going to build our model and it's working. It would work fine. Let us run this. So this implementing deep supervision is easy, not that tricky. Now we need to run the second file, UNet 3 plus with deep supervision, and it's working fine. You can see all the 5 activation function indicating the 5 different segmentation. So training this architecture would also be a bit tricky, because having one as one output and having 5 output would be different. So I'll also made a video how to train UNet 3 plus with any segmentation data set shown. But first let's study this. Now next is we need to add CGM, that is, what do we call it, classification module. That is this is deep supervision which we have implemented. Next is classification guided module, the CGM. Now this is a diagram and it would really help you to understand. So just see, this is decoder 1, decoder 2, decoder 3, decoder 4 and encoder. It predict, and this is deep supervision, it predict 5 masks. Then it take feature from the encoder 5 or the bridge, what I call it, and it has these dropout, 1 by 1 conv, adaptive max pool and sigmoid. After that it has these probabilities, so 0.6, 0.4. Then it is followed by an argmax. So here you see the maximum probability is from the 0th index. So after argmax is going to give 0, and if it is, let's say, instead of 0.6, 0.4 it is 0.4, 0.6, then this would remain 1. So now ultimately here we would have two values, 0 or 1. So let's say what it is indicating is this 0 or 1 indicating whether an organ is present here or not. So if it is 0 here, organ is not present. So this means, let's say here organ is not present, it's saying 0, but mask is predicting something. So what do? We multiply this 0 with these 5 masks. So we simply don't have any mask. So in this way it improves your performance. But let's say now the masks are predicting some tumor or some organ, and classification also says there is some tumor or organ present. So we multiply it by 1, and multiplying anything by 1 remains the same. So it does not have any effect. So in this way, adding your classification guided module would help you to improve your performance. Now let's move on to the implementation part of it. So now what do? We add this entire deep supervision code here and we remove some blocks. So first of all, what we need the classification part. First of all, let's move on to the classification after the bottleneck. Okay, so first of all, it has a dropout followed by a conv layer. So a dropout of 0.5, I think, as the paper. Okay, the value of dropout is not mentioned. I'm putting 0.5, and after dropout it has convolution layer with 2 as the number of channel. So 2 basically indicate the 2 classes, whether organ is present or not. And I'm for following the code mentioned in the official GitHub repository of this paper. You can check that code. Like if I am implementing this I'm also assuming even if you use 1 as the class and use sigmoid as the activation function, you can use threshold of 0.5. That will still give you 0 or 1 value, but I'm assuming they have done better work. So I'm for following what they have done. I'm going to paste all the layers. After convolution, we have global max pooling. What I'll do, I'll print the shape of everything so that you get to know what I'm doing. Now we're going to print the shape after global max pooling also. And I'm going to comment out these. Okay, here you can see this is the feature map 16 by 16 by 2, and after global max pooling it became, that is what it do, it applies a max pooling over the 16 by 16. So just imagine we are applying max pooling with the window of 16 by 16. So this is what it would become, and after that it is followed by an sigmoid activation function, then a argmax. So what argmax does, I've already told you. These are the two probabilities, 0.6, 0.4. So if you apply argmax, it's gonna give the index number of the position where we have maximum probability. Here in case 0.6 is the maximum, and it is at the index 0. Next we have CLS, so it add an extra dimension to this. So let me just write like this, and you're gonna know. Okay, so you can see this is the before adding new dimension. This is after this. This is just for better what do we say, calculation, because while working with any neural network architecture, shapes are really important, because you have a lot of operation, multiplication, concatenation, addition, lot of these things, and not having a proper shape would cause you an error. Now we'll move on to the deep supervision part, and here we need to implement this. See, the paper has the original paper has done some dot product bit complicated, and what I simply believe, my intention, what I'm seeing is, if you simply multiply this 0 or 1 with these masks, it's gonna do it work. So I'm gonna follow my way, not their way. Okay, so what I have done is, I'm gonna simply say it like this: just multiply the y1, the output of convolution layer, with the classification result, and same you can do, but here after upsampling, and same y3, y4 and y5 you can do. Let me paste them, y4 and same for y5. So here we have a combination of deep supervision plus CGM, classification guided module. Now we're gonna have one more output is CLS, that is the classification, and we need to give this as the input during to it. So now you must be assuming why the need of this classification guided module. Because most of your example would have all the masks, every image would have a mask, but not all data set have this. So if you have worked with like CT data, so what would happen, let's say you have a CT slice, a CT volume, and you do it and you separate it into slices, and let's say you are working for a specific organ, so that organ would not be presenting on all the slices now. So in that way, some of the slices would have a mask indicating that there is a tumor or specific organ, but other would not have. So to easy that thing, this classification guided module is used in the UNet 3 plus architecture. And we are done with this CGM. We can see CGM we can add here. So deep supervision plus CGM. Now let's say model. So finally we are done with the complete implementation of UNet 3 plus with all its component, that is deep supervision and CGM, that is classification guided module, and here you can see the CGM layers, I believe, and also these are 5 activation function indicating the deep supervision. So that's all for this video. I hope you understand UNet 3 plus, and I hope this video would be helpful to you. And if you find this video interesting, please make sure to like the video, share it, and subscribe the channel. And if you have any question, you can email me. Thank you, and please make sure to subscribe the channel.